Session. I'm happy to introduce the first speaker, Constantin Teleman. He will talk on Kramer-Wannier and electromagnetic duality in field theory.
Yes, thank you very much for the invitation to speak. Let's see, maybe it works now. I owe, I think, the organizer and the audience two apologies. First, I was very late in coming up with the title, and then I changed it at the last minute, too. Partly because it took me a long time to think of something new to say on the official topic of the workshop about equivariant case theory and related things. And then having come up with something and arrived, I saw a lot of talks about lattice models and lattice field theory, and it turns out that Dan Fried and I have been thinking about some issues related to that very recently, so at the last moment decided to ditch my old talk and prepare a new one to give today that's more in the fits maybe better with the lectures I've had so far, although that of course created a lot of additional and unnecessary effort and pain for me and probably for the audience. I think ditching a prepared talk and starting a new one is a bit like calling an election when you already have a majority. All right, so the title is Kramer-Wannier duality and electromagnetic duality. So these will be some dualities that appear in topological field theory and lattice field theory, which you can, by a stretch, you can think of it as topological as well, and it's a point of view will be a bit profitable. So this is also known as high-low temperature duality. And this will be just in the topological quantum field theory. So the finite gauge group. And while I'll focus on dimensions 2 and 3, starting. So maybe I should say start from our attempts to understand the construction of the Ising model in 2 dimensions, and what I'll talk about is what we've come up with so far, which at least attempts to put it in the context, broader understood context of topological field theories. But what I'll say, in fact, works in arbitrary dimensions. So one of our goals was to integrate, if you like, the lattice formulas with the more modern, I think, point of view in topological quantum field theory, which is based on Handel decompositions of manifolds. So maybe I will use my notes. So I think here are the key points I'd like to make. So it's going to be a fresh look at the Abelian, what I call sigma models and gauge theories, or higher gerb theories if we go to higher dimensions. And the point of it is, once you stay in the language of TQFTs more abstractly, you can dispense with Abelian, so generalize this to the non-Abelian groups. In particular, the statement of high-low temperature duality for a non-Abelian target group that we're aiming for is at least in formulation is new. I'm not sure if in substance. And one of the points that's helpful is to connect the classical duality, the Kramer-Wannier duality, to electromagnetic duality. In particular, a dictionary, which is, I think, again, known in practice, but maybe not when you read a textbook, it's not apparent, the relation between some operators that appear in the Ising model and some operators that appear in gauge theory, namely what are called the order and disorder operators. Are related, so that's why it's quickly arrow is going to come in, are related to Wilson and 't Hooft loops. An apostrophe here. Sorry? Tuft. Is the apostrophe in the wrong place?
Before the T.
It's before the T. No. Before this T? No, before that T.
First T, which is Uberate.
An apostrophe and a T. I will let this stand. I mean, no, I don't think it's profitable to debate. All right. And at the end of it, of course, there's no theorem yet. Maybe there will never be, but there certainly leads to a natural conjecture about invertibility of topological phases, which I think is something, at least something to get your hands on and trying to attempt to prove something. Invertibility of some topological phases. Okay, so this being the broad aim, so let me try to write the sections I'll cover and help me get my timing right. So one is, and with due apologies to the vast majority of the audience, I think, but because I'll state things differently, I have to at least insert the ingredients. List the ingredients as a refresher on the Ising model. And then a little quick background on gauge theory. So background on gauge theory. And finally the duality, so that and then so I think 1, 2, and 3 are I can't say the new material, maybe the new formulation at the most, but they're well-known things, well-known for a long time. And 4, that's where we came up with a new formulation in terms of TQFTs and boundary conditions. So TQFT formulation. Oh, and I didn't put my collaborator name on the board. At the beginning, joined with Dan Reed. And for us, that was our initial aim. We wanted to understand how to write all this for a non-Abelian group without having to write very complicated state sums. So in the end, you can convert what we have to a state sum formula, but the abstract formulation somehow is like the master formulation for all of that. And 5 is a conjectural picture on phases. And continuum limits. So I mean the starting point is going to be a lattice theory, and I'll start with 2 dimensions. It'll be clear then how some things can generalize. So we'll start with a surface, which it helps to take it orientable. I mean not orientable, closed and triangulated surface. And triangulation should really be a polygonation. I don't insist on things being triangles. And then there's a set V, E, and F of vertices, vertex, edge, and face sets. And we can form, based on this triangulation, we can form a chain and co-chain complexes with coefficients. So C0, 1, 2, and 0, 1, 2 are co-chains and chains. There's not a huge difference when you take a finite triangulation. The direction of the differentials, of course, is opposite. And the coefficients will be in Abelian group. So A is a finite Abelian group. And A check is a Poincare dual. And finally, we need something like the action, actually exponentiate action. That's a function, a positive even function, and we want it to have a strict minimum, I think, at 1. That's the unit. And theta check is a Fourier transform defined in a dual group. Right, and in this picture, the classical fields over which you take the path integral, the space of classical fields, are the zero cochains with coefficients in A, and then that you define a measure. We write the measure mu to a function to R plus, which sends a cochain to, so that's a map to A something, a value at every vertex, to the product over the edges of the value of theta at the cochain applied to the boundary of an edge. And I haven't oriented the edges, and it helps for that to have the function to be even, so I don't need to know which one is the end point, which one is the starting point. You could refine that. So the classical case of Ising is as A is a group plus minus 1, of course, and the function theta is e to the beta, e to the minus beta, sorry, it's actually the other way around, at plus 1 and beta at minus 1, and beta is, for reasons that are mysterious to me, is the inverse of the temperature, always positive. And then the free energy of the system, or the path integral of the theory, if you like, is the sum over all fields of the value, I guess, mu of c, so that's going to be sum over c of product over the edges of what I had written before, the theta value of the boundary of an edge, but let's write it explicitly. In our case, it's sum over maps from the vertex set to plus minus 1, all possible maps, of the exponential of beta times sum over the edges of the a value of, and I think that's a minus beta here, the plus boundary times the a value of the negative boundary inverse. Of course, the inverse does nothing in here, but for another group you want it. And of course, to get something more interesting than just this one number, you can insert operators. So you can insert point operators. You choose a vertex and the function phi from A to C, for example, a character. Phi A check for some character of A, and insert that function before you do the integral, or rather the sum. And so insert the function simply phi of A at V inside the sum, inside the path integral. And get correlations if you insert several of those, and you can start doing what I think eventually, if you go down that road, you end up doing statistical mechanics, I think, on this system. But there's a point of view I'd like to take that's closer to topological field theory, which I want to say it's a field theory for triangulated surfaces. It's a field theory. It's a TQFT for triangulated surfaces. So for triangulated circles subdivided, you get a Hilbert space which is the L2 functions on simply maps from the triangulation, or let me write functions on maps from the vertex set to A, so V is vertex set. The right inner product to put in there is not quite the obvious one. You have to correct it so that the propagation given by this action is self-adjoint. So modifying the product. In the product to get self-adjoint propagation. Back integral. And you can think of it as an approximation of some kind of physics when you have a large vertex set. But one of the questions I'll be focusing on is what's the low energy behavior of this, or what are the lowest eigenvectors for the, well, the lowest eigenspace for the propagation on this Hilbert space. And here's the classical result, which I couldn't find it. I couldn't find the exact reference, so I'll be grateful for a pointer and now also for an eraser. Maybe we'll keep the plan. Theorem is that, I'm going to call it the untwisted case, is that the case F, if the temperature is greater than a certain temperature, then as V goes to infinity, there are two lowest eigenvectors, which are the aligned states, maybe, sorry, this is AZ mod 2. I don't know if it's actually known for general A. Well, in fact, it's false. It doesn't make sense for general A because I haven't written the general action yet. Which are the functions support, delta functions support the aligned states? Aligned spins, let's say. So the maps are O plus 1 or O minus 1. Those are the lowest, just become the lowest eigenvectors, and the gap to the higher eigenvalues goes to infinity. Gap to the next eigenvalues. And then case B, if T exceeds Tc, so beta small, then as V goes to infinity, there is 1. Which is a constant function. So all classical states are weighted equally. And Tc or beta C, beta critical, is computed by the condition that this function should be its own Fourier transform insofar as possible, meaning up to rescaling by an overall constant, determined by beta is a constant times its own Fourier transform. And if I remember, beta critical has something like sinh of 2 beta critical is 1 if you solve it. All right, so now the high-low temperature duality is meant to be a duality in the theory between the large and small values of T. So on the face of it, seems impossible because we have different behavior, but simply because what I've written here is just half the picture. So I need the other half of the picture, and I need my notes.
Sorry.
Yeah.
It's not really clear to me how to take the volume, infinite volume limit.
You take V is a vertex set. I didn't take any volume. I'm just taking the circle, making it large, and you're asking about the eigenvalues of a matrix. I didn't even claim there's a theory defined. I'm just claiming something about eigenvectors.
So you change sigma essentially.
There's no sigma. It's a statement even just about the circle at this point. But you're right. That's what you want to have in mind.
Okay.
That's what you want to have. You want to say that you want to say something stronger. But even for this, I mean, I just did some very toy simulations to convince ourselves it's obviously true. But even for this, I couldn't find the exact place where it stayed with proof. But of course, what it likes to say is that the theory acquires a long-range limit, which is purely topological, and it's determined by, well, its space of states is determined by, is it a two-dimensional or one-dimensional? That's what we like to say, but I didn't say that because I'm not claiming it's not known. I just couldn't find somebody saying it clearly with all the assumptions and the proof.
So does it matter whether I'm thinking about 1D quantum Hamiltonians or 2D classical transfer matrices, or is that going to be important? Or
maybe it matters to you.
No, well, that's why
I'm saying what I'm saying that in terms of I think the statement is in terms of the transfer matrix of the propagation here. By the propagation, I mean exactly transfer matrix.
Okay. Okay. Good. So that's what
that's the statement is about. All right. So as I was saying, there's meant to be a duality between these two states, which seems impossible with this because it's only half the picture, and the other half the picture comes about because we didn't add all the freedom we have in the theory. So what we have to add is a background gauge theory to get the duality really working. No, that's the one I want to keep. Oh, by the way, I talked about point operators. I just erased them. In the Ising case, of course, only one interesting character, the sign representation for the group. So there's only one operator to insert, in effect. And that's called the order operator. So to recover low T, high T duality, need a background gauge field. And the gauge fields are finite groups, so there isn't really a gauge field. What there is a principal bundle, so you can couple the theory to a principal A bundle on the surface. At first sight, the bundle needs to be flat, of course, because A is a finite group. Flat because A is finite. And then the fields become twisted coefficients, I mean, for this. So fields become sections over V of this bundle, this background bundle. So before, a bundle was trivial. The theory had a global symmetry by the group A because of the way the interaction was constructed. If you shifted all fields by A, you didn't change the action. That, in fact, I should have said here, this is the two lowest eigenvectors of course, a regular representation of the global Z2 symmetry, whereas this is a reg rep Z mod 2, and this, of course, is in the trivial representation of Z mod 2. So now I've gauged that symmetry, so as you would say, but the gauge field at the moment is just a background field. So now you get a free energy for every choice of principal A bundle on sigma, and that isomorphism is classified by H1. So the free energy Z, instead of being just a number, is a map, a function on H1 of sigma with coefficients in A to the reals. So it's a vector in the space of functions on H1. Vector in a Hilbert space. Of H1 of sigma A, instead of being a number. Been promoted a bit. So some remarks are in order here. First I said, since A is finite, any principal bundle over sigma has to be flat. That's of course correct. But if you look at what you need to define the action, so what do you need? You have sections of a bundle over the vertex set, and you need the bundle to be defined along the edge so you can measure the difference in values between nearby points, so you can write the action because you want to write theta of the section of the boundary of the edge E. So you need to be able to compare 2 points. Certainly the bundle needs to be defined on all edges, but nobody says a bundle should be defined inside the faces. So in fact you can insert curvature, quote unquote, by allowing monodromy around faces. So here remark 1, the bundle may have branch points, the best way to describe it, may have branch points. Or curvature would be some kind of discrete curvature at the centers of faces. And the monodromy is an element of A of the group A, so labeled by vectors, the elements A in A. But of course you cannot just prescribe some points in general and some group elements and say, okay, I've defined the bundle. You actually have to specify more information, you have to specify the branched cover. Nonetheless, I mean, sometimes people are a little bit careless in physics or in some of the literature, and they just talk about disorder operators, which mean inserting a monodromy labeled by a group element at the point. So disorder operators. These punctures labeled by group elements. You have to supply a bit more information. For example, they come pairs connected by paths described up to homotopy, and you might be lucky to get away with having defined a covering. So then instead of counting or summing over you're still summing over sections of that principal bundle, branched principal bundle, I guess, fixed by disorder operators. But you've changed the vector you get, the partition function.
To defend physicists, I think what they would say is if you're careful, the careful physicists, you're changing, when the non-trivial sections in that language correspond to changing the boundary conditions. So when you introduce a disorder operator, you have to worry about what you're doing at the boundaries. And that's I think it's
you could say that, but that's not what I'm saying, because for example, sigma would be a closed surface. In fact, instead of a boundary, it'll be a bulk just in a second. But yes,
yes, you have to use this language.
I mean, careful physicists will be saying the correct thing, just in different words. I'm saying it in the way a mathematician would say. What we're defining is instead of a principal bundle, we're defining a branched cover, and you have to specify enough information. At the minimum, you have to specify that, but more information is required.
That's the way they dealt with this subtlety.
Yeah, all right.
You're worried about.
So, what's the key remark number 2? And order operators are no longer well defined on their own. Because the field at a point doesn't take values in a group, but in the torsor over the group, so you don't know what the value of the function is. Even if you chose the function in the group, the most you can do is define pairs of order operators connected by a path which is defined up to homotopy. At most, pairs of order operators connected by a path up to homotopy. Because then you can use parallel transport to measure the difference between the two sections, the two endpoints of the path. That's a group element, then you can apply a function. But now suddenly you see that there's a symmetry now between order and disorder operators. which before seemed to not exist. So now it's going to be credible that the high-low temperature duality is going to in fact interchange those. So that it becomes a precise, a possible and true statement. So KW, change them. The two types of operators. And notice what's happening just, I mean, well known, of course. The disorder operators are labeled by group elements. The order operators are labeled by functions on the group with their characters, the elements of a dual group. So the interchange will also switch the group with a dual group. We just need one extra piece of thought to understand what happens in a non-Abelian case, but it's time, I think, to state the ambient duality, which is a bit easier, but which is the boundary condition. I could add the word flat, duality in 3 dimensions. And the theorem, I don't know an author of it, seems to be folklore, but it's shown up, of course, over time, many times over again, there is a duality, there is an equivalent. Of 3-dimensional gauge theories based on the groups A and A dual. I'll say one word about how you can, the master statement that generates all of that, but let me just say vaguely given by the Fourier transform. By Fourier transform. And Poincare duality. And for example, in the space of states, it's exactly a classical Fourier transform, the vector space of states are H1, functions on H1 of sigma on principal bundle, functions on principal bundle. And this is in duality by Fourier transform of functions on H lower 1 of sigma with duals for a dual group. Is the dual group. And of course, now we can use Poincare duality to get the space of states for H check. That's isomorphic to functions on H1 of sigma to H check. So on space of states associated to a closed surface, that's a map. I'll tell you what generates the duality. It's a duality of fully extended field theories. So you can generate from one statement.
Question?
Yes.
Do these 3-dimensional gauge theories have a name that is like...
Gauge theory?
Well...
Pure gauge theory without a Dijkgraaf-Witten twist.
Lattice, lattice.
No. It's the purely topological one.
But this is a Z2. Okay, so
A is an abelian group now.
So continuous abelian group.
No, A is a finite group, finite abelian group. That's why I said flat. And this is pure gauge theory counting bundle. In a second, it'll be non-abelian. No, if it wasn't flat, it would have to be 4 dimensions. But we can take that.
Okay.
We can take it outside.
But it's Z2, say Z2.
Z2 is fine, yeah. For the Ising, it would be Z2. But it's in 3D. I mean, if people know electromagnetic duality, sometimes they're surprised because it's in 4 dimensions normally. But that's when you have curvature. This is the flat case. There's no lattice theory, but we'll have a lattice theory as a boundary condition to give things away. So these are fully extended TQFTs. So generated by, well, by two categorical objects, for example, tensor categories. By the tensor categories, vector bundles on the A with the convolution product, and the vector bundles on A check with the convolution product. And the equivalence between them is a Morita equivalence. So these are Morita equivalents. I'll tell you in a second how, but I can say it in a non-Abelian case. I'll wait for that. And so this actually is a proof of the theorem, but now let's spell out some further feature. So, addendum. So, there are no point operators in the pure gauge theory that you can write, and no gauge invariant quantities at a point. Just as we saw in the case of the gauged Ising model, you lose the ability to have operators at a single point, but if you have 2 points on a surface and the path between them, you can write something, and this is really a three-dimensional feature. So there are no point operators, but there are two obvious kinds of loop operators. There are more than two kinds, but there are two dual kinds of loop operators. Now, sometimes you can insert the path integral, which is a sum, I guess, before summing. In the Wilson loops, labeled by representations of A. And when you count bundles, you weigh them by the trace of the holonomy. Use trace of the holonomy as weight factor. And there are the, I'm going to be in trouble again. How was that? Apostrophe first. Toothed loops labeled by elements of A. And what they give is a branching for a principal bundle, and again you count it instead of flat bundles, counting branched bundles with branching specified by the group element. So count branched bundles, branch couplers instead of bundles. There are actually, the most general loop operator is a mixture of the two, but these are somehow two Lagrangians inside the space of loop operators. And the addendum to the theorem is that the duality switches the two kinds of loops. So EM duality switches the two kinds of loops. Which makes sense, but which is A and A check, so the labels get representations of A are elements of A check. It's very reducible. Alright, so that this way a statement is of duality is completely canonical, as it should be. It's a Fourier transform in the end. You just have to pursue it categorically all the way down. And now combining the two stories, I hesitate to call it a theorem because it's an observation of putting things together now. So let's call it a fact. So the, let's say, Ising model based on A with gauge background field is a boundary condition for three-dimensional pure gauge theory, flat gauge theory. Is a boundary condition for pure 3D gauge theory. So that means, for example, if you have a three-manifold with boundary, a surface boundary, the surface boundary, to be able to write the Ising model, has to have a triangulation on it. You've chosen an action theta for the model. To that you can assign a number, which is going to write the Ising partition function as a vector, as a function each one of the principal bundle on a surface, and pair it with a vector coming from the rest of the three manifold, which actually counts the ways in which to extend the flat bundle on the three manifold, and the result is a number. So in other words, once you put the boundary condition on the boundaries, behaves like closed manifold, gives a number. A number counting flat bundles weighted by Ising action. Flat bundles and sections over the vertices, sorry. That's what goes in Ising action. Weighted by the Ising action.
The coupling beta in the Ising case, where does that come from in the 3D case?
It doesn't exist. It's a part of a boundary condition.
Okay, so beta is just some zero, or I mean, what's
Beta, beta would have to be, no, it doesn't exist. It's not a data of the theory, it's a data of the boundary condition. You have to choose an action, a function theta on A, to define a boundary condition. Every choice of theta gives a different boundary condition.
I see, good.
So boundary condition requires you to choose extra structure on the boundary, a triangulation. It's no triangulation invariant, that's why it's not a topological theory. If you refine, you're not going to get the same thing.
I see, good.
And it requires you to have chosen the action theta. I mean, otherwise you don't have it yet. All right. And now that's a little theorem now that requires the proof that the statement is obvious now. We have a duality of three-dimensional theory of A and A check. I mentioned the high-low temperature duality, and the statement is that they match. So EM duality in 3D extends to a duality of boundary conditions between A and theta and A check and Fourier transform Ising models. And the Fourier transform temperature is in fact the dual temperature in the classical Ising case. And under this duality, that's a cute part. This duality. So Wilson loops don't have to be loops anymore once you have a boundary. They can be like, they can end on the boundary. They have to end at vertices, and they end namely at order operators. The pair of order operators connected by loop. Since the loops may end, they're not loops anymore. May end at vertices on the boundary, and they end at order operators. Remember, they're usually classified by characters of A, points of A check. These are functions on A. And two loops and the faces on the boundary. And there are these order operators. And these are, of course, interchanged by duality. All right, so since I'm close to done, I'm probably not sure what I say about 5. Maybe I can erase this now. So let's say something about non-Abelian case and the abstract generalization. Because I don't know of any computation high dimension with the abstract generalization, but at least we know how to state things completely cleanly. So what about non-Abelian G? So in fact, electromagnetic duality works for non-Abelian groups G, but the dual theory is no longer given by a group. That's the price you have to pay. Remember, yes, it's still up on the board. And this abstract formulation was an equivalence of, Morita equivalence of tensor categories. That was at the root of the duality of gauge theories. And that generalizes to a non-Abelian group if you reformulate the second category in some way. The group A check does not exist anymore. So no group A check. But note that the category of vector bundles on A check with the convolution product. So this is like a multiplicity space where every irreducible representation of A can be also described as the category of representations of A with a tensor product. And indeed, there's the Morita equivalence. This goes back to lots of people, maybe Ostrich, I think, often maybe even before that. I want to put Ostrich names. It could be older. There's the Morita equivalence. Of categories, of tensor categories from vector bundles on G with convolution with representations of G, the tensor product.
G is finite here.
G is a finite group, so fine. Yes, I'm not going to say anything about it. I mean, it's not completely well-defined topological theories for when G is a Lie group, although you can still do something for U1 or so on. You can still make some statements. But a lot of quantities become infinite. So this time it's no longer even, it might not even be plausible at first because, you know, these are different numbers of symbol objects in this category. So they look very different, but the bimodule which generates it, so that is induced by the bimodule, by the category of G vector bundles on G, where G acts by translation. And of course, the equivalent as a category to vect, but not as a category with a. You have obvious actions of the two categories on this guy, which you don't have on vect, but not as a bimodule. So electromagnetic duality works. You can repeat the discussion of a 't Hooft-Wilson loops, that's all well known. Then the question becomes, well, how do you write the lattice boundary theories, the Ising model and the dual Ising model for something which doesn't exist? And so reduced to this statement, this is a tautology, but when you write the state sum formulas for the TQFT, from the two different sides, they look very different. So it is actually a theorem that from this you get equivalent TQFTs. So you can get the state sum formulas for Dirac-Viro constructions in all these cases. So one remark. Dirac-Viro sounds very different. So the only thing missing, if I want now to recover the more general theorem of boundary condition, explains how you construct some kind of Ising model based on this tensor category ref G. The question So it's no longer, there's not going to be a classical story anymore, just like in this case. There's not going to be a space of fields where you can write a measure and integrate that, because this category is not going to be a group-like object. So it's not obtaining it by quantizing something finite. So it's really an algebraic construction now. So in fact, a lot of the work was to try to avoid writing the state sum explicitly and understand what works. So because time is short, I'll tell you a general answer. 2 weeks ago, I was at the Simon Center with Dan. Reid finally managed after 2 days to write on the board something which looked like a plausible state sum for the Ising action here. I have a picture on my iPhone, but I will not try to reproduce it because first, probably not quite right, and second, I would fill up the time and wouldn't be so enlightening. So instead, let me tell you the abstract picture which allows you, which tells you there is a state sum formula for such things, and generalized vastly. So, abstract picture. Oh, I'm sorry. I have to do that, but I didn't finish the duality statement, so sorry, I skipped a bit. So, I'd written this theorem about the gapped states, and when I introduced the gauge thing, I forgot to give the other half. Well, let me do it at the end, or I'll tell you later if I have time. This is another half of the theorem describing the gapped states in Ising, which makes the duality actually work. But I forgot to state it involves the non-trivial bundles on the circle. When you put them all together, duality works. Sorry. So let me just continue here. Abstract picture for Ising-like lattice models. So what's the data? And the point is it's all generated from the three-dimensional theory, topological theory. Surprise. So a three-dimensional TQFT, let's call it T, and this was pure gauge theory. That is my son. I have 5 minutes. And if you remember, when we looked at the boundary, we took sections of a principal bundle at the vertices. Well, taking sections of the bundle at the vertices, or fixing the bundle at the vertices, is a boundary condition for gauge theory. It's called the gauge fixing boundary condition. So a 2D boundary condition. Let's call it beta 1. Gauge fixing. But we only fixed the gauge at the vertices. We didn't do anything on the faces. We did something on the edges. That will come next. But the face really did nothing when writing the action. And doing nothing actually is doing something if you think about it really hard. Because there's another boundary condition of pure gauge theory, which is the free boundary condition where you do nothing. So another, a complementary boundary condition. Beta 2, the free boundary condition. And complementary, I mean something very precise, that home from one to the other is just the trivial theory. So condition is home in the theory achieved in the boundary condition beta 1 beta 2 is trivial. Trivial meaning 1, not 0. And what that means, let me just draw the picture and compute that. You're doing gauge theory, let's say on an interval, and fix the gauge at one end and do nothing at the other end, and now count what you have. The count comes out to be 1. You have no information at all. You fix the gauge at one end of the interval, let it free at the other. That is the statement. So it's free fixed gauge theory. So this condition tells you that there is a canonical domain wall or defect between beta 1 and beta 2. And let's draw a quick picture of what's happening on the surface. What you thought was a lattice theory is something that's actually handle decomposition. Start with the lattice and open a textbook in differential topology which tells you how to put a vector field, a triangulation, how to put a vector field on it which proves the Euler-Poincare-Hopf theorem. There will be a way to do that. Have a critical point on each face, at each vertex, inside each face, on each edge. And that point comes from a Morse function, in fact. It's a canonical Morse function you can write. And the Morse function in this case would have level sets. I can write the Morse function for you. I think it's 1 minus cos x minus y cos x plus y. But the level sets would be, well, let me draw them here actually. And well, it's a conventional, but here you'll have the minimum cells, you'll have the maximum cells, so the maxima are in the centers of the faces, the minima are the vertices. And the critical points of index 1 are right here, where the green defect lines intersect. Alright, so now I've colored the boundary in this way. With two colors of a defect, the boundary of a three-manifold, and have a defect line between them, and I almost have a meaningful picture in field theory except for the fact that defect lines intersect. There's no meaning to self-intersecting defects in field theory. They have to be smooth as well. So all I can do is erase the intersections and leave white circles there. White means it's a gauge theory. And now I have a meaningful way of coloring the boundaries. Now you want to think this blackboard is a surface, there's a three-manifold going in behind that carries the gauge theory. And the boundary of this surface, the boundary of the three-manifold has been subdivided. Parts are colored by a boundary condition, another boundary condition, or actual boundaries. And what's the meaning of that? Well, you have to understand the meaning of the circle. You have the circle with gauge theory, with gauge fixing on the two red arcs, and freak boundary conditions on the blue arcs, and it's a surface in a three-dimensional theory, so to that there is always assigned a vector space. And here's a computation that's easy. It's the functions on the group. Gauge theory. So each circle is a place where you can insert a function on the group, and guess what? We have a function on the group which was called theta. This is the action inserted at each edge, and now this is a, if you like, the TQFT, abstract TQFT reading of the lattice theory. So again, you have a surface sigma. You thicken it a bit to a cylinder. You leave gauge theory on most of it, and using a triangulation on one side, now subdivide it into, and subdivide the surface into red squares, blue squares, defects in between, and every time defects cross, you have to insert the action. And that is a picture, meaningful picture in three-dimensional field theory, gives a number, that is the Ising partition function. And now the theorem becomes the duality of gauge theory T in this case interchanges the free and the fixed gauge fixing boundary condition. I think I'm going over time. So this is the abstract formulation of the lattice partition function. And duality. Well, the final thing I want to say, because I won't have time to explain it, it's very tentative anyway, is we think of that we want two-dimensional honest theories, not boundary conditional three-dimensional theories. Well, there's an obvious way to get to that by coloring the other part of this interval with a complementary coloring, complementary group and the Fourier transform. So you want to think of this as the quantum version of a polarization of a three-dimensional field theory. And the polarization, thanks to a lattice, can now be scattered across the surface, and you can put the conjugate polarization on the other side. And we assemble the two pictures this way. This is very reminiscent of how Chern-Simons theory and WZW models work, where the chiral WZW is a holomorphic boundary condition for Chern-Simons theory, and the full WZW is obtained by taking two copies, a copy and the conjugate, and gluing it together with the Chern-Simons glue in the middle. So I think there's a lattice model now for, if you like, for this picture, and my inclination would be to say that it is this doubled picture which is much better behaved in the continuum limit than just half of it, because working just with the usual lattice side is a bit like trying to discover a complex structure out of a lattice, whereas what comes out naturally, I think, is a full non-chiral theory out of the two copies of the Ising model at dual temperature. I'll stop here.
We don't have much time. Do you have a quick and short question or comment?
What were you going to say about the spectral gap?
Oh, right, so for the non-trivial bundle, there is again the ferromagnetic state, that means you put a twisted sector in the ferromagnetic state, there is no ground state. There are no aligned spins, and the energy of the lowest ground state is much higher than the energy of the ground state in the trivial case. So 0 is the lowest energy, the gap state. The 0 vector here. But in the paramagnetic phase, high temperature, the twisting doesn't matter, and there is one ground state, which is again the constant function on all spins. And now if you put all the twisted and the untwisted circle together, you find that you get, so in the ferromagnetic state, you get regular representation of Z mod 2 on the untwisted case, and 0 in the twisted case. The paramagnetic state has just the trivial representation of Z mod 2, and I don't know why I think there should be a sign representation of Z mod 2 in the other now. And so the duality interchanges somehow. This decomposition and this decomposition are not dualized. So in the high temperature phase, you're spreading over, you're spreading the two states over twisted and untwisted bundles. In the low temperature state, you're spreading it over two characters of Z mod 2. So that's how duality works, which is indeed how it should work, because it will exchange the monodromies with the representations of the group. So that's quick. Yeah.
So you explained to us how the lattice Ising model can be viewed as a boundary condition of pure Z2 gauge theory. Does this also survive the continuum limit? Is there a way of seeing the Ising?
So I think the continuum limit I'd like to claim here is that this becomes, if you you double it, then this becomes the chiral fermion, anti-chiral fermion, and fermion Chern-Simons. The slight difficulty with making the statement precise is that the three-dimensional theory has to change for that to be true, because it requires central charge. To which, again, the counter argument is that this story is only going to appear for surfaces with the two sides combined, so you're not going to see a central charge.
Why do you, because if beta is not at the critical point of the Ising model, already you don't have a chiral theory on the boundary anyway.
Correct.
On
yes.
one, so maybe you don't even have to double this to see this. I mean, there's a whole thing in topology.
No,
if you take like the torus,
I just don't believe there will be a limit of just one side.
yeah.
Because there are topological theories in at least lattice theories, but like the toric code, for example, look at the boundary there, and it's a gapped boundary and all that. It's not a critical theory. So you have left and right movers on the boundary.
Yeah, so I don't know that example. The only example I thought a bit was this, and I think that one of the puzzles was that the low high temperature duality is changing a sign of the mass, and this kind of behavior is not replicated in the free fermions. So one of the things I want to explain is why. Why in the continuum limit, so to speak, this Fourier transforming of a duality doesn't seem to be reproduced. And our answer is not reproduced because what you're seeing is actually a coupling of dual temperatures together. So all you're doing, what the duality is doing, if you like, is switching the sides. And in other words, doing nothing. Switching the sign of the mass gives an isomorphic theory in that case, which becomes not homomorphic, but a field theory that switches left and right movers in the formal case. But on the one-sided discrete theory, it has a dramatic effect that you actually notice, and on the free fermion it doesn't. So why? And the answer, well, because it's a combination of the two copies at dual temperature. That's the explanation.
Yeah, we don't have time anymore. Let's thank speaker again.